Review video number 14 is all about refraction. So one of the first things we need to know is refraction is just the bending of light. Okay? There's something called the index of refraction. And there's a list of these in your reference tables, and they're denoted by the letter N. Okay? There's no units. Okay? And it's basically proportional to the optical density of the material. So the more optically dense the material is, the higher the index of refraction is. And you can calculate the index of refraction from the equation N equals C over V. C is the speed of light in a vacuum, and V is the speed of light in that substance. And because it would be a meter per second over a meter per second, those would cancel out, and you would not have any units on your index of refraction. Okay. So the thing that we use for calculating index of refraction is called Snell's law. And it's N1 sine theta 1 equals N2 sine theta 2. Now, I'm going to draw a picture here in a minute to demonstrate this. But essentially, it's easiest to keep from getting them confused if we use this first section as anything that is incident, okay, where the ray is coming from. The second thing is anything that's refracted, okay, what the light is going into. So if this is our medium interface, let's say we're going between air and water, nice easy one. Air on the reference tables has an index of refraction of 1.00, water is 1.33. And let's say we have a light ray coming in to that interface, and we draw our normal line. We measure this angle here, this would be theta 1. That's the incident angle. And let's say we measure that to be 25 degrees. And they want to know, what's the angle of refraction as it enters into the water. So the first thing we know is that because the index of refraction for water is larger, and knowing this equation here, N equals C over V, if this goes up, velocity is going to go down, right? So index of refraction of water is larger, so the speed of light in water decreases. So you can think about slowing down and kind of falling towards that normal line. Okay? So right away we know that the angle of refraction should be smaller than our incident angle. So you can plug in everything that you have into Snell's law, N1 sine theta 1. Oops. Equals N2 sine theta 2. Okay. So 1.00 sine of 25 degrees equals 1.33 sine theta 2. That's a theta 2 in the corner. Ran out of room. So then we can solve for theta 2, and if we do the math, once I find my calculator on my desk somewhere, not so sure where it went. Let's try this one. So it'll be sine of 25 divided by 1.33. And you do the inverse sine of that. And it comes out to be 18.6 degrees. Okay? So just like we said, it should be a smaller angle than our incident angle. Now, also remember that the frequency remains constant. So if we know that the speed of a wave is wavelength times frequency, if the frequency of the light stays constant and it goes into a more optically dense medium, so the velocity goes down, that means that the wavelength decreases as well. Okay. Now there's several other equations that we can talk about here. Well, one more thing real quick on this side. If, let's say, we switch these around. Actually, let me draw a new one here. Let's say we're going from water into air. Okay. So we draw our incident ray. There's our normal line. Now, because we're going into a less optically dense medium, we bend away from the normal. Okay, that light speeds up, it's going to bend away, and sometimes they'll just ask a more general question like that. Now, if it happens to be the exact same index of refraction, then no refraction would occur at all. It would just continue right through. Now there are a few things on the reference tables that do have the same index of refraction. For example, glycerol and corn oil have the same index of refraction. So if it was a medium interface between glycerol and corn oil, okay, and this ray came in, we drew our normal line, it should be dashed, then it's not going to refract at all, and those angles should stay constant. It should be the same. Now, if we're going from a larger, let's do air and water again, larger index of refraction, so from in the water out into the air, okay, we get internal reflection that happens. So it goes here and boom, bounces back out. Okay, if you tried Snell's law, you would get an error for that. And one of the last things I want to talk to you about is something called the critical angle. So air, water, okay. Here's our normal line. Here comes the light, and the critical angle is where it doesn't refract, it doesn't reflect, it just simply travels along the medium interface boundary. Okay, so one of the things we know there is that this would be 90 degrees, and we solve for this critical angle. Since it's incident in the water, that becomes our N1. We still use Snell's law. Okay, except now we know that this is water, 1.33 sine of the critical angle, because that's where we're coming from, equals N2, which is air, sine of 90, because this angle here to the normal to the light ray is 90 degrees, and you can solve for that critical angle. Okay, and the last thing, dispersion. Dispersion is where you have some sort of prism, okay, and you have white light. Let's see if I can do this here. It's going to be kind of hard. Well, let's try this. Okay, so we have white light coming in, even though that's a black line. I get that. And then as it hits this, it separates the white light into the spectrum. Okay, it's bending the colors at different angles, at different amounts. So blue bends more than red. So blue would be refracted the most and coming out. Okay. Then you would have all the other colors of the spectrum in between these. Red would be bent the least. Comes out this way. So you get this nice rainbow effect. Okay, and that's dispersion. It's basically just taking the colors of the white light and dispersing them into their own individual colors. And that's it. There's going to be just 2 more videos. They'll be on modern physics. The first one will be on energy of electrons, photoelectric effect, things like that, and the last one will be on subatomic physics. Almost done.